Today we're doing partial fraction decomposition.
Yes, sir.
Along with De Moore's theorem. That's actually 2 hours worth of material, but we'll start on partial fraction decomposition.
Yes, sir.
Now, this is an interesting subject. I've actually had 8th graders that get this subject. And
yes,
yet,
sir.
it only comes into application when you're doing integral calculus. That's it.
Really?
Never do you run into it before you get to Calc B.
Wow.
Once you get to Calc B, it's extremely important. But why they even teach it before then, I'm not sure. And it's pretty complicated. It's fairly easy at the basic level. Let's do number 1.
All right.
Do you understand that?
Yes, sir. You just separated among the factors on the denominator?
Yeah, in other words, if I had, say, 8 over x minus 2 plus 4 over x plus 3, the way we would do that problem would be to find a common denominator, which is x minus 2 times x plus 3. And we would have a numerator of 12. Well, no, we wouldn't. I'm sorry. Let me take that back. Okay? But partial fraction decomposition has everything to do with how you add or subtract fractions that have variables in the denominators.
Yes, sir.
So, we're going the other way.
Yes, sir.
And before we go the other way, let's just make sure you know how to do this. How do you do that?
You would multiply 1 over x minus 3 times x plus 4 over x plus 4, and then you would multiply 1 over x plus 4 times x minus 3 over x minus 3.
Tell me what the common denominator is.
X minus 3 times x plus 4.
And don't ever multiply that out.
Yes, sir.
There's a reason for that. What's the numerator on the left side?
X minus 4. X plus 4.
What's the numerator on the right side?
X minus 3.
All right. So you know how to add fractions.
Yes, sir.
Even when there's a variable in the denominator. Good. Because that's what you're doing here is the reverse of that.
Yes, sir.
Okay. So I know it's something in the numerator over x minus 2 plus something in the numerator over x plus 3.
Yes, sir.
So if the right side becomes this, which it's going to. In other words, that's how you handle the right side.
Yes, sir.
Now, I'm going to put an A there and an A there. Or a B there.
A B there. Okay.
Okay?
Yes, sir.
So, what this tells me is 8x minus 1 has to equal a plus b, because the denominators are the same. In other words, I have ax minus 1 over x minus 2 times x plus 3.
Wait, would it be a times x plus 3? Or would it just be a?
No, you're right.
Okay, I wasn't
No,
sure
you're
about that.
absolutely right. Thank you. So, here, let me restart this. So, the numerator has to be a times what you said, x plus 3, plus b times x minus 2. That has to equal that.
Because the denominators are equal.
Exactly. In other words, the denominators are x minus 2 times x plus 3.
Yes, sir.
Now, when you get to this step, there's some nice techniques you can use. Shoot. Sorry.
Yes,
Let's see if I can recreate it from memory. So what I say, 8x minus 1 has to equal a times x plus 3 plus b times x minus 2. Is that what we had?
yes, sir.
Okay. Now, the trick in solving this is to choose values of x that make a,
Yeah.
in other words, if I choose x equal minus 3, what's the equation, the next line of that equation?
B, E, wait.
I'll start with the left side.
Okay. All right, a times 0,
Okay.
or is just 0, plus negative 5b, or minus 5b.
Notice that gives us an answer. For b. Is b equal to?
Yes, sir. Wait. B is equal to 5.
Okay. So we know what b is equal to. Hold on.
And this only works with problems with 2 variables.
Yeah, this works with most of the problems you're going to run into. There are other techniques to use when it gets a little more complicated.
Yes, sir.
What am I going to, in other words, this equation has to be true for all values of x. So what's the next value of x that I want to plug in?
2.
Okay, so 2 would give me 16 minus 1 over there. A times 5. What's a equal to?
3.
Now we've solved it.
Yes, sir.
In other words, starting from the original, 8x minus 1 over x minus 2 times x plus 3 equals 3 over x minus 2 plus 5 over x plus 3.
Yes, sir.
Now, the next thing you would probably want to do is solve the right side of that equation to make sure you get the left side.
Yes, sir.
Well, common denominator is going to be x minus 2, x plus 3, and I'm going to have 3 times x plus 3 plus 5 times x minus 2. You with me?
Yes, sir.
If you do that multiplication, you end up with 8x minus 1.
Yes, sir.
In the numerator.
Yes, sir.
Okay, that just merely shows you that you did it correctly.
Yes, sir.
Okay, so what we have is, oh man, I keep doing this. Hold on. Okay. So if we're decomposing this, what was A?
Yes, sir. A was 3. And then 5 over x plus 3.
That will be a true statement.
Yes, sir.
Now, why do we care? The reason we care is because when you get it to calculus, it's extremely difficult to take the integral of that function.
And when you say take the integral of that function, what do you mean?
Calculus is differentiation and integration.
Yes, sir.
When you integrate, it's extremely tough to integrate. But it's fairly easy to integrate things that are being added together. It's extremely difficult to integrate things that have a denominator that's being multiplied together.
Oh.
Just remember that.
Yes, sir.
When we're talking calculus, it's much easier to work with stuff that's being added or subtracted than it is stuff that's being multiplied.
Yes, sir.
And we've separated this thing where there was multiplication going on in the denominator into two things that are simple addition.
Yes, sir.
And integral calculus says that the integral of the left is equal to the integral of the right plus the integral of that. And it's very easy to integrate that, and it's easy to integrate that. What's tough is to integrate what we started with.
Yes, sir.
I'm going to assume you're going to take calculus at some point in your life.
Yes, sir.
You're smart enough that you should.
Yes, sir.
Definitely should. And this is going to come into play. It won't come into play until about halfway through calculus. And calculus is tough enough, but this is pretty tough also. And this gets tougher. We did the simplest one of all. So,
yes, sir.
Try number 2, another simple one.
All right.
What is that going to equal? That's the first step.
So that is a over x minus 4 plus b over x plus 1.
Okay. So now, work on the right side. How would you add those two fractions together?
Find the least common denominator, so that would be the least common is x minus 4 times x plus 1. That's going to be the denominator. And then you will have a times x plus 1 plus b times x minus 4. And yes.
Like that.
That's right.
Okay, and we know that that's equal to x minus 29 over
Right.
minus 4 times x plus 1. So the denominators kind of cancel out, right?
Yes, sir.
So let's just get rid of those.
That's right.
What we have is x plus 29 equals a times x plus 1 plus b times x minus 4.
Yes, sir.
Now, some of these are easy such that you can make up values for x that will let you solve for b, and you can make up values for x that will let you solve for a.
Yes, sir.
They're not all like this, but this
Yes,
is
sir.
an easy one. So give me an x value.
-1.
So I got negative 30
Equals
b
negative.
times negative 5.
Yes, sir.
What's b equal to?
6.
And what are we going to choose for x to solve for a?
4.
So when x is equal to 4, we have what? Minus 25
Is equal to 5a.
5a. A equals
-5.
so I can just substitute those. A is
Yes,
negative 5. Somehow I got in a different color. Plus b of 6.
yes, sir.
Now, if b ends up being a negative number, then it's the first term minus the second term.
Yes, sir.
Okay?
That's right.
All right. So that's the easy way to do it. The key thing is that once you get to this step, that equation has to be true for all x.
Yes, sir.
Because that's true, you can make up values for x that happen to cancel out the a term, and then you can solve for b. And you can make up values for b that cancel out the b term, and you can solve for a.
Yes, sir.
And get your answer.
Yes, sir.
Those are the easy ones. Let's see if we can find a harder one. Well, this isn't really a harder one, but we'll give you a shot at it. X plus 34. What should I do to that denominator? When you're talking partial fraction decomposition.
So that's going to be x minus 6 times x plus 2.
Now, what's the right side of that equation look like?
A over x minus 6 plus b over x plus 2.
So, keep going. Solve the right side.
Denominator is the same as it is on the left.
Okay.
And they're going to be two fractions, a times x plus 2, and then the other will be b times x minus 6.
And that all has to be equal to what?
X plus 34.
Same problem as before.
That's right.
You can choose x equal minus 2. That lets you solve for b. You can choose x equals 6. That lets you solve for a.
Yes, sir.
All right. Now they get I don't know if yet they get harder. Do something with the denominator.
So that's x times x minus 4.
Equals what?
That is a over x plus b over x minus 4.
Same kind of problem as before.
Yes, sir.
So the numerator is going to be this. That has to equal this. You can pick an a, or you can pick an x to eliminate A, and you can pick an X to eliminate B.
Yes, sir.
Okay, so I'm not even going to go through that because I can see you understand it.
Yes, sir.
Let's look at 5. It's going to be a little harder.
Yes, sir.
Over that denominator. What's that going to be equal?
That is going to be A over x minus 1 plus B over x plus 2 plus C over x minus 3.
Solve the right side.
So that is A times x plus 2 times x minus 3, B times x minus 1
plus B
plus B times x minus 1 times x minus 3 plus C times x minus 1 times x plus 2, and that is all equal to 4x squared minus 15x minus 1.
Good. Now, this is a little tougher because there's 3 variables, A, B, and C. So I can't really pick an X that makes A, B, and C go to 0.
Can you pick an x that'll make 2 at a time go to 0?
Well, it's a different technique. Let's talk about this. Let's go ahead and multiply out the right side.
All right.
Hold on a second. I'm going to need more room. I'm going to start from the top. You don't need that anymore. So, solve the right side of the equation.
So, do you want me to do, okay, like that. So that's A times x squared minus x minus 6 plus B times x squared minus 4x plus 3 plus C times x squared plus x minus 2.
Very impressive that you can do that quickly. Very good. Okay, and that is equal. Now let's distribute that.
Yes, sir. So that's a x squared minus ax minus 6a plus b x squared minus 4. How would you want me to put that? 4bx or 4xb, or doesn't matter?
I would leave the capital letter in front.
Okay, b 4x plus 3b plus cx squared plus cx minus 2c, or c2.
Now, shoot. What was that all equal to? What was the left side? Oh, I'm looking at it.
4x squared minus 15x minus 1.
Okay. Now, what we want to do is distribute, which we did in this bottom step. Gather all of the x squared terms. What do we have?
Do we want to
just gather
the x?
That's an x squared term.
Yes, sir. A x squared minus b plus bx squared plus bx squared. I was looking at a different term. Plus cx squared.
Put a parenthesis on that. Gather all the x terms.
That is minus ax minus b for x plus cx.
And gather all the numbers.
That is negative 6a plus 3b minus 2c.
Why am I not seeing the, oh, I see it now. Okay. Since that has to be equal to this,
Yes, sir.
we can use a theorem that equates the coefficients.
Yes, sir.
Here, I'm going to rewrite this right side over here. That's x squared times a plus b plus c, correct?
Yes, sir.
Minus x times a.
Would that be negative a?
4b minus c.
Okay, that's right.
This term over here? I think it is.
Yes, sir.
And the constant is minus 6a. I'm going to put parentheses there. Minus 3b plus 2c. The only thing I do is make sure that I don't change it going from there to the blue.
Yes, sir.
And I haven't. Okay. Now we're in a position to equate coefficients. This is by far a harder technique than the other one, because you have to do all these extra steps, and then you're going to have to solve 3 equations and 3 unknowns. So
yes, sir.
Whenever you find that you can use that first technique where you can let x equal some number that zeroes out a or b, do that. That's far easier.
Yes, sir.
Okay, now, what can I say? I've got this equals what I got at the bottom.
Yes, sir. So a plus b plus c is equal to 4. A plus 4b minus c is equal to 15.
And
6a minus 3b plus 2c is equal to 1.
now, you have 3 equations and 3 unknowns. So we're not done yet. We got to solve those 3 equations and 3 unknowns.
Yes, sir.
Once you solve them, you will have A, B, and C. And you will have your answer.
That's right.
Do you know how to solve 3 equations and 3 unknowns?
We pair up.
This is not the easiest problem. In other words, we're tackling 3 or 4 different difficult math concepts today with these partial fractions. That's why I can't believe they were taught in 8th grade, but they were.
Wow.
I know. I couldn't believe it at the time, and I still can't believe it. Considering that it is not needed for anything until you get to Calc B, which most people aren't going to take until college. Some people will take Calc B as a senior in high school. But teaching this in 8th grade is crazy, crazy. All right.
Yes, sir.
How do we solve? Well, we might as well talk about this because this is something that's important.
Yes,
How do
sir.
you solve 3 equations and 3 unknowns?
Um,
Let's call that equation 1, 2, and 3.
we can start by, is it eliminating a variable?
Yes, you want to eliminate, here's the process. You're going to create an equation 4 and an equation 5, and
All right.
both of these are going to have the same variable missing.
Okay.
So the first step is to pick what variable you're going to eliminate.
Let's do C.
Good. What's the first elimination of C?
All right. So with equation 1 and 2, the C's are already opposite, so we can just add those together.
So you get 2a plus 5b equals 19.
That's right.
Now, you have to use 2 different equations, but you still have to eliminate C
Yes, sir.
to create equation 5.
That's right.
So how can I eliminate C in equation 5?
We can multiply equation 2 times 2 and then add it to equation 3.
Go ahead, add it.
So that will be 8a plus 5b is equal to 31.
I forgot to multiply that side by 2. Very good.
Yes, sir.
Okay, now we have 2 equations and 2 unknowns. That's pretty easy. That's a lot easier
Yes,
than
sir.
3 equations and 3 unknowns. How do I solve this? 4 and 5.
Multiply equation 4 times -1 and then add it to equation 5 to solve for A.
Let me just suggest an alternative because it kind of saves a step. And that is, in addition to being able to add equations, you can always subtract equations.
Yes, sir.
I don't need to take that step. What if I take equation 5 and subtract equation 4? What do I get?
Yes, sir. 6a is equal to 12.
A equals
2.
Now I got to solve for all 3 variables. What do I do next?
Yes. So you would you get 3 new equations?
No?
Or
In other words, go back into one of equations
that's right.
4 and 5, and that will let you solve for B. Do the simplest one.
That's right.
That one.
5b is equal to 15. Plugged it back into equation 4.
Okay.
And b is equal to 3.
Okay, so we got A, B, and now how do we solve for C? Go up into the simplest equation you have.
C is equal to -1. Plug them back into it.
Now we have our answer.
That's right.
And notice that it was a lot tougher. In other words, the moment you have 3 denominators in your partial fraction decomposition, it's the same difference as solving 2 equations and 2 unknowns as opposed to 3 equations and 3 unknowns.
Yes, sir.
It's that much harder. Okay?
Yes.
So what we have is 4x squared minus 15x minus 1 is equal to 2 plus 3 minus 1 all over the same denominator.
Yes, sir.
Well, not over the same denominator. Like this. I think you knew what I meant.
Yes, sir.
Now,
That's right.
why is that so valuable to do? Because if I said integrate that, I would have no idea how to do it.
Yes, sir.
I cannot believe how hard it is to integrate functions. It's harder than Chinese long division. Okay?
Wow.
But
Yes,
if you
sir.
split it up into these three things that are all being added or subtracted, then it's really easy to integrate that. And it's really easy to integrate that. And it's really easy to integrate that.
Yes, sir.
So that's the whole point of this, is in an attempt to do calculus, you have to be able to integrate complicated functions. And
Yes, sir.
one of the first easy techniques is to split it up. In other words, to decompose the fraction that you're looking at into the sum or difference of linear fractions. Notice
Yes,
that this is linear. That happens to make for a very easy integral. It's 2 natural log of x minus 1. The second one is 3 natural log of x plus 2. The third one is 1 natural log of x minus 3. So I integrated it almost instantly. Whereas if I was trying to integrate this, I got to go through this entire process. This is a 15-minute problem. But that's the way calculus is. Calculus is tough, trust me. And this happens to be one of the harder, even when they teach calculus. I got a calculus BC student right now. He does not have to do partial fraction decomposition. That is not part of the Calc that is not part of the Calc AP, Calc BC test, which is the hardest test in high school.
Wow.
They don't have to do this. Because we've only touched upon it. It's going to get much harder. We go through some of these problems. Now, I'm not really sure how much sense it makes for you to go to the extreme difficult levels of this. I'm happy to go as far as we can, but I gotta believe that if you can master these, and these, you'll do just fine on any exam you're taking.
Yes, sir.
If you're trying to learn math at the greatest degree of difficulty, then I'll teach you the harder part of this. It's kind of
the harder part.
This gets a lot harder. When you start getting denominators like that, it gets a whole lot harder.
Could
we can
you
just go
explain to me why
order here? And that's what I would suggest. Let's make sure you can do problems like this. I think that's the hardest thing you're going to have to do. You're not going to have to do problems like this until you get to calculus.
Could you explain to me why when a factor of the denominator is used twice, like in 23, it's basically x squared plus 1 times x squared plus 1.
Yeah.
Why, when you do the partial fraction decomposition, you have to do the whole
What's
Let me
the
see.
common
Well, since
What's the common denominator?
x squared plus 1 squared.
Correct. Notice that I did not multiply both denominators together. That's the difference. In other words, when I had 1 over x minus 1 plus 1 over x plus 2, the common denominator is always that times that.
Yes, sir.
But if you have a linear factor that is being squared, it is the common denominator. In other words, the common denominator here is the right denominator.
Yes, sir.
So it's a over x plus 1 plus b over x plus 1, squared. That's also squared. Let's do this one. Let's do that one.
All right.
So what I have is 4x cubed minus x squared plus 4x plus 2 equals, and this is the tricky part right here, it's really x squared plus 1 plus b times x squared plus 1. They're both squared. That is the common denominator.
Would they both be squared?
Yeah, let me do the left side.
Or would it just be that A has the factor when it's used once, B has the factor when it's used to the second power?
If I'm adding them together, that's the common denominator is x squared plus 1, the least common denominator. Here,
That's right.
Here, let me put up another example here. What's the common denominator?
X squared.
Aha! I didn't multiply them together, did I?
So it would be 2x over x squared plus. Okay.
So that's the difference. You don't always multiply those denominators together. If one is a factor of the other, then it's just the biggest one that is the common denominator.
Okay. So the B term would remain the same, but would it be A times x squared plus 1 over x squared plus 1 squared? Or,
Well,
because you started out with that example with 2 over x,
yeah.
and then you had.
Well, hold on a second. I'm going to have to look this up because this is where it gets really complicated. This is a repeated linear factor. No, it's not even a repeated linear factor.
It would be quadratic.
It's a repeated quadratic factor. And when you get those, if it contains a non-repeated irreducible quadratic factor, that is a non-repeated irreducible quadratic factor. So,
Yes,
I believe this is a over x squared plus 1 squared plus b over x squared plus 1 squared plus c times x over x squared plus 1 squared. This is where it gets hard, where you have to add the cx. It's not clear why we have to do that, But the rules are, if you have a quadratic repeated, a non-repeated irreducible. Notice that x squared plus 1 is irreducible. It does not factor.
Yes, sir.
The only solution is x equals I, plus or minus I.
Yes, sir.
So it's all imaginary. That is called a non-reducible repeated quadratic.
Yes, sir.
That's when you have to bring in the cx in the numerator.
When the denominator is a quadratic factor, we have to put the cx in there because the numerator has to be 1 degree less than the denominator.
I think so, yes. That's a good way to look at it.
I think I have that when you're adding when the numerator has to be linear, would it be, I think the numerator would have to be linear on all of them. Would it have to be ax plus b? Because that's what I have for making the numerator linear.
Well, I'm going to solve this. To be honest with you, it's been so long since I've done this that I'm not 100% sure, but we can sure find out, right?
All right.
Let's try it. In other words, I can tell from these three denominators that my common denominator is that.
That's right.
Okay, so let's start with this. 4x cubed minus x squared plus 4x plus 2, what's that going to equal?
Is that a...
Yeah, I've done this wrong already.
So it would be a times x. Okay, yeah.
We're going to end up with an x to the fourth. We don't want that. So that tells me immediately I got problems. In other words, a is going to be times x squared plus 1 times x squared plus 1, right? Hold on. Am I doing something wrong here? Let's see. Yeah, because it has an x plus 1 squared. You know what? If we're going to work on these harder ones, I need to look at it a little bit more. I'm not sure I'm giving you the correct solution. I'm certainly willing to do that. But it's been long enough since I've done these that I'm not 100% sure how to handle these when you have a non-repeating irreducible quadratic in your denominator.
Yes, sir.
So before I give you advice, I want to look that up and I want to research it.
Yes, sir.
All right. So let's halt these for the moment.
All right.
What did we get down to? We got down to number 20.
I think that was
We're looking at 23. We didn't do all the ones in between. You'll notice that 7 can be factored into 3 factors.
That's right.
You're going to have 3 denominators. It's all going to be A, B, and C.
That's right.
8 can be factored into 3 linear factors. That's going to be an A, B, and C.
That's right.
9 can be factored into x minus 1 times x minus 1.
That's right.
It's going to be an A and a B.
That's correct.
Same with 10. Well, 10, maybe you're going to have 3 denominators, x, and x plus 2.
Yes, sir.
I think that will solve that one. The only time it gets a little harder is when you get to 13. Because
13.
you actually have a repeating. Now, hold on a second. Let me look at that again. Actually, 13 should be easy. That's x plus 2 times x plus 2 times 2x minus 1. So you're going to have an A, a B, and a C.
Yes, sir.
It's only when you get to 14 that you have an A, a B, and a CX. In other words, once you run into a denominator that has an irreducible quadratic,
Yes, sir.
actually, now that I look at 14, I'm not even sure that's true. That's x plus 1 times x plus 1. In other words, that's not irreducible. I can reduce that. It's x plus 1 times x plus 1. That's an A, B, and a C. Let me look here. 15, same thing. 16, same thing. 17. 17 has what we call an irreducible quadratic. X squared cannot be equal to 1. You cannot factor that.
That's right.
Same thing with this one over here. That is where I believe you need to be. You have an A, a B, and a CX.
Yes, sir.
Then you go from there. And that's where I need a little bit of refreshing to be able to show you how to do those. Although I'm not sure you really need to know those. I would have a hard time believing they're going to give you very many problems like that on a test in high school. Maybe once you got to Calc BC, you'd get a problem like that. Even then, believe it or not, you don't. I'm tutoring a Calc BC on the AP Calc BC exam, which is a college BC Calc course. You don't see problems like this. That's higher degree of difficulty.
Wow.
Yep. It's so hard. There's not very many people by the time they get to Calc BC that have ever done these kind of problems. They certainly don't remember back to 8th grade, and most 8th graders don't get this. Most people do not get partial fraction decomposition until they get to Calc B, because there's no need for it. You never need to do it for any other reason. It's only when you're trying to take the integral of something. When I'm trying to integrate it, I cannot integrate what I'm looking at. But if I can split it up into these partial fractions, you can integrate it. In other words, it's easy to integrate this. It's really hard to integrate this.
Yes, sir.
In other words, the top one is the integral of A plus the integral of B. So if I can do that and that, much easier than doing that. That is really hard, the integral of A times B.
Yes, sir.
All right. So we've gone about as far as we can go on partial fraction decomposition without me doing more research.
Yes, sir.
Let's take a look at your other page, which involves de Moivre's theorem. We don't have much time, but we can kind of get into it.
Yes, sir.
Let's look at this one right now. Oops. I meant to do that. Hold on.
3 cube roots of negative 27i.
Okay. let's talk about this. We'll end today's session with De Moivre's theorem.
Yes, sir.
Notice that's the root.
Yes, sir.
God, I just don't have enough room on this page. I need either a bigger drawing tablet or a bigger monitor.
So it's basically R to the 1 over n cis the angle plus 360k.
That is the beauty of De Moivre's theorem. In other words, I can find the root of anything. I can find the 6th root, I can find the 3rd root.
Ah.
Because all I got to do is take that complex number and convert it to this equation. We were doing that the other day. Our complex number was this, correct?
Yes, sir.
So that's really this.
That's right.
Okay. What's R?
Is that 27? Or?
R is actually the square root of 0 squared plus 27 squared. So yes.
Okay. So that would be 27.
We look at this equation. We figured out R. What's n?
N is going to be 3.
Okay. The 3rd root. And k is just, that's an integer that goes from negative infinity to positive infinity. But it's an integer. It's not a fraction. In other words, it's 1, 2, 3, 4, 5, 6.
Do we start with 0 and go to 1, 2?
Start with negative infinity.
Okay.
In other words, k can be negative 1, negative 2, negative 3, negative 4.
Yes.
Notice that when k is any integer, the cosine of theta over n is the same. Well,
yes, sir.
That's not true. I'm sorry. It's been a while since I've done this one also. Let's figure out what theta is.
Yes, sir. All right.
That's the only thing missing. In other words, we have R, we have N, we know what K is going to do. The only thing we're missing is theta.
Is that 270? Or do I have that wrong?
Well, let's see. What were we doing the other day? We were doing the cosine of theta equals...
it was, oh boy, what was that?
X over, let's see, R cosine of theta equals X. So, it's
okay.
And sine of theta equals Y over R. So, cosine of theta equals X over R.
So cosine is equal to 0.
Because
sine,
X is 0? Yes.
Sine is negative 1. So it is 270. Because we have negative 27 over 27.
Yep.
So the sine is negative 1. All right.
Okay. So now it's all we have to do is solve it. So theta is 270, right?
That's correct.
So we've solved for r, n, and theta. The only thing left to do is to plug it in.
So we can have
I'm going to write
27.
So we got the third roots of 27 times cosine of 270 divided by 3
Yes, sir.
There is going to be your third roots of minus 27i. Now, if we look at that, all of that is, you can get all of those out of a calculator.
Yes, sir.
Right?
That's right.
Third root of 27 is 3. We got the cosine of 90 plus 2 pi over 3.
That's right.
Yeah, I'm not remembering exactly what. I think you can work. I'm not sure. But let's ignore that for a moment, which I'm not sure we can do. I think that actually gives you other solutions. But if we could ignore the k, I know how to deal with it. You plug in k of 1.
That's right.
Okay? If you plug in
Yes,
k
sir.
of 1, this is equal to some number.
That's right.
If you plug in k of 2, you get a second number. You plug in k of 3, you get a third number, and they're different. Now,
And
at some point, when k is equal to 4, it might be the same as if k is equal to 2.
Ah.
Okay? So
Yes,
k does count up, but when it recounts beyond a certain number, you don't get new solutions. You get the same solution.
Yes, sir.
So we're going to let k go from 1 to 2 to 3 and see if we get different answers. But whatever answer we get will be the third root of minus 27i. And what does that mean? It means that whatever answer we get, if we multiply it by itself 3 times, we will get minus 27i.
Yes, sir.
Remember when I was talking about the 8th root of 1? That is a complex number. And it's a complex number that if you multiply it by itself 8 times, you will end up with 1. That's what the 8th root of 1 means. If I want the third root of 1, then I'm looking for numbers that if you multiply themselves by themselves 3 times, you'll get 1. If I'm looking for the square root of 1, I get plus or minus 1. There's 2 solutions. If you multiply either one of those by itself, you get 1. So the square root of 1 is easy. It does not involve complex numbers. But the moment you start looking for the third root of 1 or greater, there might be a 16th root of 1. Is all that would mean is whatever that root was, multiply it by itself 16 times, you get 1.
Yes, sir.
So complex numbers introduce all kinds of strange things that we're not used to.
Yes, sir.
Like having more than 2 roots of the number 1 or 4. And De Moivre's theorem is perfect for figuring those out, because we're going to take our imaginary number or real number, regardless, and use this theorem, and n can be anything I want.
Yes, sir.
The 8th root of the number, it can be the 3rd root of the number, it can be whatever.
Yes, sir.
Now, why one would want 8 roots of the number 1, I don't know. But that's where your higher mathematics starts.
Yes, sir.
Garrison, I'm going to let you go. I know you got stuff planned for today. And yeah, this is tough stuff. But thank you for sending it to me in advance, and please continue to do that as long as we're going to be doing stuff like this.
Yes, sir. I will.
All right, Garrison. You have a good rest of your day, and I'll talk to you later.
Yes, sir. Have a nice day.
You too. Bye-bye.